Hello, everyone, and welcome to today's webinar titled How to Limit Patient Harm from Erroneous Results, QC Strategies Based on Risk Management. I'm Susie Valdez of LabRoots, and I will be your moderator for today's event. This educational web seminar is sponsored by Bio-Rad Laboratories. I want to invite everyone to participate by submitting your questions during the presentation. To do so, simply type them into the Ask a Question box located on the far left of your screen and click Send. Any questions we do not have time for during the webinar will be captured and responded through a Q&A list that will be posted next week in the Event Resources box, which is located below the Ask a Question box. You will also be able to download the presentation handouts from this event resource box starting September 17th. If you have any trouble seeing or hearing this presentation, simply contact us in the Ask a Question box and we will address that issue immediately. As a reminder, this presentation is educational and offers free PACE continuing education credits. Click on the Continuing Education Credits tab located at the top right corner of your presentation window and follow the instructions to obtain your credits. So let's get started. I now present today's first speaker, Mr. John Yundt-Pacheco. John performs research in quality control and patient risk issues for the Informatics Discovery Group at Bio-Rad Laboratories. John has had the opportunity to collaborate with laboratories around the world, developing a practical, real-time, inter-laboratory quality control and proficiency testing systems. As an innovator, he has developed numerous ideas, leading to over 35 laboratory-related invention patents around the globe, all providing new and cutting-edge solutions for our diagnostics laboratories. For a complete biography on Mr. Yundt-Pacheco, please visit the Biography tab at the top of your screen. John, welcome. You may now begin your presentation, sir.
Thank you, and howdy, everyone. I appreciate you attending our webinar here, and my goal is to talk a little bit about and perhaps give you an understanding of why we should be thinking about risk-managed QC. So we'll spend a little bit of time distinguishing risk-managed QC strategy design and why that's necessary. And then we'll look at some of the things that I want you to take away from this are, first of all, to be able to identify what do we mean by patient risk managed QC strategy design. What does that mean? How do you do it? And one of the key elements, as you'll see, is that it is based around the severity of harm model for risk management. And hopefully everybody's going to come away with an idea about how do you set that severity of harm category for an analyte. And then we'll talk about when we have a QC design, what are some of the things that we can change that will change the risk of that QC strategy. And so specifically, I want you to come away with a couple components of what can I do to minimize patient risk in a QC strategy. So those are some of the three key takeaways that I'm hoping everybody is going to leave this with. And in order to get there, we're going to start with an overview of risk-managed QC design, and why is it important? And then we'll talk about this ISO risk model and severity of harm. And then how do we put all these things together and actually compute a risk management index? And so what we'll see is that a risk management index, RMI, is a very concise way to summarize exactly what is the strategy that I have, what's the risk that I have in my test method when it comes to controlling the risk of patient harm from erroneous results. Well, once we've got that foundation underway, then we're going to take a look at how do I actually use this to solve QC design problems with risk management techniques. And we're going to use a tool called Mission Control in order to do that, which is basically a calculator that will walk us through the computations that we need. And then finally, we'll sort of summarize what the impact of this type of risk-managed QC design approach is. So, why do we want to move to risk-managed QC? What are the benefits of doing that? Well, I would say the primary benefit is that risk-managed QC focuses on the patient. Conventional QC methods, where we are focused on things like metrics like the probability of error detection, are primarily focused on the instrument. So our QC strategy design revolves around how do we determine if there is a problem on the instrument. And while that is certainly something that we're concerned about, but it doesn't take into account things like how many patients are being tested, what's the utility of the clinical utility of the test method in question. And there are many things that it simply doesn't consider when our focus is primarily on, is there a problem with the instrument? So a patient-focused approach, we have the primary metric is, what's the probability that we're producing erroneous results that are going to harm a patient? And while those two things may seem like they're similar, they're very, very different. So when we start focusing on the probability of producing erroneous results, well, that depends on how many patients are we testing in the presence of an erroneous result, and things like what's our relationship between the quality specification and the test method performance? How does test method reliability play a role? What are we doing with these actual results? Are we using them in the context of other biochemistries, or are we making a decision purely based on this result, like we might do with perhaps something like an infectious disease result, where a majority of, particularly if we were looking at, say, a molecular infectious disease result, where a majority of the decision is made purely based on that result. And then, of course, the other thing we have to consider is the number of patients that we're evaluating between QC events. And this approach also, one other benefit that it has is that it doesn't assume that we have uniform precision across the analytical range. So almost none of our test methods for qualitative clinical diagnostics have the same analytical precision at a low concentration as they do at a high concentration. And that's something that we have to take into account when we're looking at designing QC strategies. Okay, well, what exactly do I mean by a risk-managed QC strategy design? Well, we start with trying to determine what's an acceptable level of patient harm. Now, at first blush, that may seem a little disconcerting. What do you mean we have an acceptable level of patient harm? Well, you know, the reality is that if you test enough patients, you are going to produce erroneous results. And if you produce enough erroneous results, you are going to cause some level of patient harm. So our goal needs to be that we are keeping the level of patient harm to an acceptable level. And so the way that we determine that acceptable level is based on the clinical utility of the test method. How are we using the results? And then we consider things like the quality specification, test method performance, how frequently are there failures in the test method, what are we actually doing with those results, how many patients are we testing between QC events? And we can use all of those things to compute the predicted probability of producing patient harm. And then we want to find QC strategies where the predicted probability of patient harm is less than the acceptable level of patient harm. So this relies on the ISO model for acceptable risk. In ISO standard 14971, the application of risk management to medical devices presents a model for risk management and determining what is an acceptable level of risk. This same approach was also used in EP23, the CLSI laboratory quality control based on risk management standard. They both use this same risk model, and the concept is pretty straightforward. You use the risk model to assign a severity of harm category to each analyte. And that category of harm is based on how are we using these test results in a clinical setting. And each severity of harm has an associated maximum probability of patient harm. So if we have a certain level of patient harm, of course, the greater the harm, the less our tolerance is going to be for it. And then that acceptable probability of patient harm gets used to determine just how many erroneous patient results can we tolerate. So let's take a look at what those severity of harm categories are. Well, they are divided into 5 categories, starting with negligible and going all the way up to catastrophic. And it should make perfect sense to everybody that, if we have negligible harm, the consequence to the patient might be inconvenience or temporary discomfort. Well, we have a lot higher tolerance for inconveniencing our patients than we do for causing something like serious harm where it's impairment that requires professional medical intervention. And so you can see these different categories of increasing severity of harm, and then we have a corresponding probability of patient harm that's associated with that, where we start at negligible, where we've got an acceptable rate of 1 in 100, and then with each severity of harm, it drops by a factor of 10. So the maximum acceptable probability for negligible harm or inconveniencing a patient is 1 in 100. And then that drops down to 1 in 100,000 for critical harm or 1 in a million for catastrophic harm. So that then gives us a way to actually determine how much harm is acceptable. And it's based on the utility of the actual test method itself. So the severity of harm, if we think about the basic idea is that the more harm we have, the more severe a harm is, the less tolerance we have. So just in my little example here, you obviously have a lot higher tolerance for touching bumpers with the car in front of you than actually damaging the car. And of course, but even having a fender bender like the one in the middle, you have a lot higher tolerance for that. Then you end up in a scenario where your car is completely inoperable and it's going to take some serious help in order to make that work again. So that's the idea behind the severity of harm concept for QC strategy design. Okay, well, so what we want to do is we want to focus on how do I determine what's my probability of producing erroneous results? And there is a way that we can do this computationally. So if I have that list of things that we talked about earlier with a total allowable error, that's the TEA, test method performance and QC strategy, and the test method reliability, well, we can estimate what our probability is of producing erroneous results. So the way that we do this is that we compute the probability of erroneous results as the probability of producing erroneous results added to the probability of producing erroneous results when we're out of control. So that's kind of how we divide up erroneous results. We can produce erroneous results when everything's working fine, and we produce erroneous results, or can produce erroneous results, when we have problems. So first we'll look at how do we estimate what that probability of producing erroneous results is when we're in control. Well, here is an example of the distribution of measurement error. So if I start off with 0 measurement error, you can see that in the center of the graph here, you can see that my distribution is not actually positioned over 0. And that's because we have some measure of bias in our system. And then just in this depiction, we have the limits set by the total allowable error. So we have a lower limit of the low limit of total allowable error and the upper limit of total allowable error. And then we can see in green, you can see that our measurement error distribution is a little past the upper limit of total allowable error. So all of the distribution that falls outside of those total allowable error limits, that's going to be the probability that we have a result that is erroneous. All right, and there's a way that we can compute that. So if I've got my performance metrics, basically what are the means and SDs that correspond to the QC lots that I've evaluated for this material, for this test method. When I've got a total allowable error specification, well, then I can estimate just what's that probability that we were just looking at. What's the probability that's contained in these tails? And so I can then take that probability and actually compute what is my rate of producing erroneous results when the test method is working properly. And I can also look at how does that change as my percent of, as my error rate goes up. So if I look at a plot here, what I'm looking at is my percent unreliable. What's the percent of my results that are going to be unreliable given the size of the air condition that I'm experiencing? And so what we can see here is that as the error rate starts to increase, it doesn't have a noticeable impact on the percent of unreliable results or erroneous results that I'm producing. But when I get to a certain threshold, as the error size increases, so does the number of unreliable results that I produce, until eventually I get to an air condition so large that every test that I produce in the state of this air condition is going to be erroneous or unreliable. So this is one of the key characteristics that we want to look at when we're trying to determine what are the implications of measurement error and what happens when measurement error increases. How does that impact the patients that I'm testing in the presence of that error? Okay. So now, we've kind of presented a model for in control. Now let's talk about out of control. And unfortunately, estimating the out-of-control erroneous results are quite a bit more complicated. And the reason for that is that, first of all, they depend on, as we just saw, what is the size of the air condition. So the number of erroneous results that we're going to produce directly depends on the size of the air condition, but it also depends on how long is it going to take us to determine that, how long is it going to take us to detect that we have an air condition? So our primary goal for detecting that is our QC strategy. And our QC strategy consists of the number of patients tested between QC events, and for each QC event, how many QC materials am I testing, how many QC specimens, and what kind of a QC rule am I going to use? Well, another thing that we need to consider is that we can categorize erroneous results into two different categories. So some results are correctable and some results are final. So if we look at this little cartoon of our test method here, each vertical slash is a patient being tested. The diamonds are QCs. So I test a bunch of patient specimens, I test QC, my results are accepted, so I continue testing. And then I have an out-of-control condition. So in the depiction here, I have an upwards bias. The mean of my results has increased, and it's increased to the point that I have some results that are going to be erroneous. So now I'm producing results, some fraction of the results that I'm producing are outside of my total allowable error limits. Well, that's indicated with those two red asterisks. And then I have this first opportunity to detect this out-of-control condition, but I don't. Why? Well, unfortunately, statistical quality control is probabilistic. And so our QC rules do not have 100% probability of detecting an error. And so in this case, we didn't. So you can see that this error condition is not so large that it's pushing every specimen result outside the quality specifications, only a fraction of them. And now I've passed QC. So we categorize an erroneous result that's produced, and then we pass QC as a final result. Because once we've passed QC, we don't stop and look for erroneous results. We simply continue testing because we don't think anything has happened, because we just tested QC. So erroneous results that are produced prior to an accepted QC are final. We're never going to have the opportunity to correct them. And so we can see we continue testing because we don't realize there's a problem. And then finally, after the second QC event, we finally have a QC rejection. So when we have a QC rejection, we can stop and then take a look at the results between the rejected QC and all the patients that were tested back to the last accepted QC, and see if any of those were erroneous and then correct them. So when we design our QC strategies, what we really want to control is we want to minimize the final erroneous results. So that's what we're looking at. Now, this depends on what's our probability of error detection. Well, as I said, you don't have certainty that your QC strategy is going to detect an out-of-control condition. Each QC rule has a characteristic power curve, and that tells me what's the probability that I'm actually going to have a QC rejection based on the size of the out-of-control condition. Now, there are two aspects to this. We have small errors are unfortunately difficult to detect with our QC systems, and it may require multiple QC events. So that's the bad news, is that it's very hard to detect a small error with our QC. Of course, the good news around that is that because it's a small error, it's not likely to have a lot of impact on our patient results. Conversely, we have large error conditions. Well, those are easy to detect, but they have a larger impact on the actual quality of the results that we're producing. So given those two scenarios, let's take a look at what the impact is here. So I've got power curves here for running two QCs for a 1-2S QC rule, a 1-3S, and a 1-4S. And the way we evaluate these is that we look at the size of an error condition, and when we see the intersection between the power curve and the size of the error condition, we can then see what is the corresponding probability that we're actually going to reject. Well, this gives us a metric that we look at a lot, which is called, for a given error condition, what is our expected number of QC events to detection? How many QC events is it going to take before I actually get a rejection? And this is simply the inverse of the probability of error detection. So in this example that we were just looking at, if you were using a 1-2S rule, we would detect a 2.5S error in basically about one QC event. If it was a 1-3S error, it would take us, a 1-3S QC rule, it would take us 2 QC events. And if we were using a 1-4S rule, it would take us almost 8 QC events. Well, so that then would lead you to think that why would I want to do anything besides a 1-2S rule? Because that's going to have the lowest number of QC events to error detection. And we'll talk about why that's not necessarily the best choice always. But here is a graph of when we look at the expected number of QC events to error detection. So this starts off high when we don't have any error in the system. And that's because even without the error in the system, we still have a probability of a false rejection. And what this is showing us is that we want that to be high. So in this case, we're over 100 QC events between false rejections. And then as our error condition grows, it becomes quicker for us to detect it until finally, now this looks like it plateaus at 0, but it's actually plateauing at 1. So once we get to where this flattens out, call it somewhere around 7% error, as soon as we run QC, we're going to detect it. And then as the error condition grows, of course, we're going to detect that as well with just a single QC evaluation. Okay, well, the reason that we don't want to always just use a 1-2S QC rule is because of false rejections. So the false rejection rate is what's our probability of a QC event that's going to reject when we are in control. We would call this a false positive. So our false rejection rate, we want it to be as low as possible because we are getting noise from our QC system with the false rejections. We don't actually have a problem, but the QC is rejecting, which means we have to stop and we have to troubleshoot. We may have to shut down testing until we determine that there is no problem. So on that QC power curve, that false rejection rate is what's the probability of rejection when the size of the error condition is 0. So we're looking right up at this region of the power curve. And just to give you an idea of what the implications of this are, is that the false rejection rate for a 1-2S rule is basically 1 in 11 QC events. So that means if you're running 20 chemistries and you're using a 1-2S rule on all 20 chemistries and you're doing 2 QCs, you would expect to have multiple rejections even when everything is in control every time you run QC. Compare that to if instead I could use a 1-3S rule, where now I'm at 1 in 188, and if I could use a 1-4S rule, I'm at 7,000, almost 7,900 QC events. So what this means is that we want to use a QC rule that has the highest possible number of QC events rejections, because that will really cut down on the number of problems that we have in the lab. So given that, what I want to do is I want to find a QC strategy that is going to have that has enough power of error detection, but is going to have a low false rejection rate. And what I really am interested in looking at is finding a QC strategy that has an acceptable number of erroneous final results for an error condition. So how do we do that? Well, because we've already talked about the number of erroneous results that you're going to get depends on the size of the error condition. So what we do is we go across a large range of error conditions and compute what these final erroneous results look like. When we do that, you end up with a graph that looks something like this. So as the error condition starts to increase, so do our number of erroneous results that we're producing. But now what we're looking at here are final erroneous results. So if you recall from the other graph that we looked at, let me go back to it real quick here. When we look at just the number of erroneous results, well, that just goes up until it plateaus and it never gets lower because, of course, you know, as the amount of error condition grows, so does your probability of producing an erroneous result. But once we start looking at this definition of final erroneous results, what we're looking at is how large of an error condition can I have that I produce an erroneous result and still pass QC? And this, fortunately, it has a maximum. Why does it have a maximum? Because at some point, as the number of erroneous results grows because the size of the error condition is growing, eventually I'm going to get to the point where I'm going to start detecting that error condition. So it's no longer going to be a final erroneous result. And eventually when the size of the error condition gets large enough, well, at that point, then I'm not going to produce final erroneous results because I'm going to catch it, and those would be correctable results. Okay, well, let's start putting this together here. So we've talked about a way to compute our predicted probability of producing erroneous results. But what we really care about is what is our predicted probability of harm caused from erroneous results. And now the conservative approach would be to simply say that every erroneous result can harm a patient. But that's probably not true for the most part, for most analytes. So for instance, you know, it's very likely that every erroneous albumin result does not cause patient harm. Why? Well, first of all, we are probably considering albumin in the context of other results and other biochemistries. And if you have a result that's really way off, then that would cause the clinician to question the validity of that result, and that doesn't necessarily result in patient harm. So we have this probability of actually a conditional probability of harm given an erroneous result. That probability of harm given an erroneous result is going to be 1 if you assume that every erroneous result causes patient harm, but it could easily be much lower than 1 based on the quality specification and the clinical utility of the result. Well, now we've talked about how we can compute a predicted probability of harm, and then we've talked about how do we find the acceptable probability of harm using the severity of harm model. Well, we define a patient risk management index as the ratio of predicted probability of harm divided by acceptable probability of harm. This is we call the RMI, the Risk Management Index. And if that's at 1 or less, then you have managed risk. And it allows us to assess exactly what the risk of patient harm is under a lot of different circumstances. So I can compare that. I can easily see, am I managing my risk of patient harm? Even though I may have very different circumstances, I may have different rates of failure, I may have different severities of patient harm, I may have different patient volumes that I'm testing. All of that gets wrapped up together in one single metric that will tell us where are we when it comes to risk management. So let's take a look at how we actually use this. So here, I've got an example for a glucose procedure. And these are all the metrics that we've talked about. So we've got a quality specification of 10%. I'm testing 100 patients per day. I have 2 QC events that I'm using with 2 levels. Here's my statistics for the QC, my performance statistics, and the QC rule that I'm using. Well, I've determined that for glucose and the way that the results that I'm producing are being used, that the severity of harm category is serious. So that maps to an acceptable probability of harm, a maximum acceptable probability of harm of 1 in 10,000. And then I also have a reliability here where my mean time between failures is 90 days. So if I put all of these metrics into this calculator called Mission Control, it's going to compute what my risk assessment is. And in this particular case, I really want to consider 2 outcomes. First of all, I want to see what is my RMI. So in this case, it's pretty low. It's 0.153. And I can also see that most of that risk is coming from the out of control side, but it's still very low. And my in control RMI is about half of my out of control RMI. Now I can also see that, based on my QC strategy, I have an expected time between false rejections of about 52 days. Okay, so I have risk managed QC here, but what I would really like to do is take advantage of having such a low RMI. So this is the RMI curve at when we have 0 error. This would be the in control risk is at 0.05, and then I take the area of the curve here in order to compute my out of control RMI. And when I add those together, I get 0.15, and you can see that my RMI, which is this blue dashed line, is well below 1, which would be in control, which would be risk managed QC. Okay, so what can I do with this? Well, my expected time between false rejections is 52 days. Now, that's not horrible, but glucose is not the only thing that I'm testing. And so what I would really like to do is take advantage of this low RMI and see if I can lower my false rejection rate. Well, if I first try a 1-3S rule, I end up with an RMI of 0.26, which is certainly better. But you know what? I'm going to go all the way up to a 3.5 QC rule. And when I do that, my RMI is still 0.73. So I still have managed risk. But let's look at what this does for us. So if I'm using a 3.5 QC rule, now my expected time to false rejection is 537 days. So I've basically increased by a factor of 10 how many days I'm going to go between QCs, between false rejections. And I still have managed risk. So this is one way that you can use a low RMI. We can choose a QC rule that has a much lower false rejection rate. And even though that does increase our risk, we still have managed risk, but now we have taken advantage of our capacity to dramatically increase the number of days that we go between false rejections. Okay, let's take a look at another example here. So now I've got a sodium procedure. I'm testing 600 patients a day with 2 QC events. I'm using a repeat 1-2S QC rule. My severity of harm rate is serious, but here I've determined that really we have a pretty high tolerance for sodium results that are outside of this quality specification. And I have a lot of failures on this test method. So my sodium procedure does not have a very high reliability. When I put this into the system and evaluate it, well, I have unmanaged risk. My RMI is 1.41. Now, not only is it 1.41, but when I look at the decomposition here, my out of control RMI is over 1. So that means that, what does that mean? Well, this is what this curve looks like. We need to do more QC because my out of control condition is causing too much risk. So in this case, and last time we took a look at what happens when you change QC rules, but in this case, I'm already using about as powerful a QC rule as I can use. So instead, I need to look at changing the number of patients between QC events. And so what we're going to do in this case is we are actually going to do more QC events to drop the number of patients from 300 between QC events down to 150. Well, when I do that, I end up with an RMI of just under 1. So I'm right at the verge of, I still have risk managed QC, but now I'm actually, I am not above, I don't have unmanaged risk. My expected time between false rejections is not at 26 days, but at least I've managed to detect air conditions more quickly, which reduces my risk. And so this would be the final design that we might use for something like this. So with these examples, this just gives you a couple of examples of how would you use risk managed QC strategy design. So the number of patients between QCs, the QC rule itself that I'm using, these are all factors that are going to play into what is the actual risk that I have of producing erroneous results. So using a risk managed QC strategy design, I can, using the way that the results are used clinically, to determine what is my acceptable level of patient harm. And then I can compute what my probability of producing erroneous results are and use that to estimate my predicted probability of harm. And then that gives me an idea of what kind of QC do I need to do to make sure that my predicted probability of harm is going to be acceptable. And so some of the things that we have to consider are what's the QC strategy, specification, the QC strategy itself, how frequently am I doing QC, what QC rule am I using, how much QC, and then what is my test method performance? Because the test method performance is going to affect all of these things. And then I also, if I think about when I'm looking at my out of control estimate of how many erroneous results are produced when I go out of control, well, it depends on how frequently am I going out of control. So we have to have an estimate of what the test method reliability is. And now I also have to consider patient volume because when I go out of control, how many patients are going to be impacted? Well, that depends on the number of patients that I'm testing between QC events. And now the other thing that I want to point out here is that unlike conventional QC design, risk-managed QC design allows you to reduce the false rejection rate with additional QC. So that may not be obvious, but when you are in a scenario where your expected time between false rejections is simply too low, well, if I do more QC, I can increase that. So the more QC I do, that becomes a management decision. If I want to decrease my number of false rejections, I increase the amount of QC. Okay, so in summary, we use the way that a test is actually acted on clinically to determine our tolerance for producing erroneous results. And then based on that, we try to find a QC strategy that is going to have a predicted probability of harm from erroneous results that is going to be below the acceptable probability of patient harm. And we can represent those relationships with a risk management index, an RMI, that makes it very easy for us to tell whether or not we have managed risk and what the implications are. An RMI of 1 is managed risk. An RMI of 2, you have twice the acceptable level of risk. And so we can then use the RMI to find suitable QC strategies that are optimized for patient risk and false rejections. Thank you very much.
Thank you, John, for that great presentation. We will now start the Q&A portion of this webinar. And if you have any questions you'd like to ask, please do so now. Just simply click on the Ask a Question box located on the far left of your screen. So let's get started. We already have quite a few questions coming in, John. Our first question from our audience member is, how should harm be categorized when there are multiple clinical applications for an analyte?
Thank you. That's a great question. So we have to consider if we only have one test method. So let's take, for instance, we look at something like glucose. And that test method is being used both for screening and it's being used for therapeutic monitoring. Well, you could say that the severity of harm category for those two different clinical scenarios is going to be different. Well, but we only have one test method, so we have to pick the most conservative severity of harm, meaning we would pick the highest severity of harm for the various clinical scenarios.
Thank you for that. And is there any reference for risk in general by test, since all the laboratory measures the same analyte?
So in general, there's not an actual there's not just one reference. And the reason for that is that the way that patients are treated based on results from a test varies in clinical settings. And so there's not just a universal reference. Now, we have working with labs to try to categorize how they are ranking severity of harm for different analytes. That's a work in progress. But even with that, you really have to consider the way that results are used in a particular clinical setting in order to determine what the severity of harm is.
Thank you, John. And what should we do when we have no quality specifications available, like a molecular testing or serology?
Okay, yeah, that's kind of a tough one. So all of this depends on having a quality specification. And in a lot of circumstances, there's not universally agreed on, well, I guess most circumstances, there's not universally agreed on test specification. I would say for something like a molecular test, where, if you're looking at something like PCR, you would use some kind of a specification around when would the results have a different implication. And so maybe when there's a threefold change or something like that, that you might consider that. In general, the basic idea is you want to set a quality specification on when would the clinical decision change based on the performance of the result.
Thank you. And I want to thank our audience members. These are great questions coming in. John, does someone need to design their QC for each analyte? And how can they manage that in a lab?
That's a great question. Yeah, the logistics of this. So first of all, in a perfect world, if you do QC design for each analyte, that's how you optimize things. So the more QC designs that you can tolerate, and where this gets particularly tricky is that not only do you need different QC rules for different scenarios, you also need different QC frequencies. And so logistically, this can be a real challenge for a laboratory. Most laboratories probably can't tolerate more than 3 QC schedules. However, I think the solution would be eventually there is instrumentation that's available today, and there's more instrumentation that's coming that will allow you to set QC strategies by analyte, and then the instrument just takes care of it. So if I want to say I want to do QC for glucose every 7 patients, then I can do that, and it just happens. But it absolutely is driven by the logistical considerations of the laboratory. And just in general, the more specific QC design that you can do, well, and that's going to be the more optimized your set of solutions is going to be. But as a starting point, it has to be based on what's logistically possible for the laboratory.
Thank you for that. And our next audience member asks, our lab report patients' results all through the day. How can I manage the risk?
That's a great question. So what that means is that they're not holding results until the next QC. The ideal scenario is that you don't release results until you've passed QC, but that is not actually in a lot of scenarios. That simply does not happen. And so what you have to look at then is the design consideration that we talked about still works. You simply have to be aware that the risk goes up when you are releasing results, because your opportunity for correcting them may be diminished. And so the other thing to look at is, okay, even though we're releasing results all through the day, what is the actual time that it takes for somebody to actually review a result? So if it's routine that results are reviewed in, say, 4 hours after they've been released, and we're doing QC every 3 hours, then this is not a consideration. But if results are being reviewed, say, within 5 minutes of release, and I'm doing QC every 4 hours, well, then my risk is absolutely higher, and I don't have the luxury of looking at all of these correctable results. The other thing that I would say is that you have to be aware then that you may have to issue corrections much more frequently than you otherwise would, because if you have a failure and you've already released those results, well, now you don't have the luxury of correcting those before they're actually released. And so under those circumstances, you have to be prepared and make sure that you don't go to too many patients between QCs so that it would overwhelm your ability to correct a scenario where you've had a major failure.
Thank you so much. And we have time for one more question. When I have a 1.3S error, but my results are still within my total allowable error limits, can I report my patient results?
Thank you. That's a great question. So the first thing I would say is that the fact that you have a 1.3S error is not what you need to be looking at. What you need to be looking at is, what is your designed QC strategy? So if your designed QC strategy is that you have a 3.5 standard deviation error is when you would reject, then you wouldn't pay any attention to a 1.3S error. So the actual QC rule that is designed is what you should be paying attention to. Now, certainly if you have a rejection, so let's say, for instance, that your designed QC is a 1.3S rule, and you have a 1.3S rejection. Well, at that point, what I would do is take a look, and we determine that 1.3S rejection was actually indicative of a problem in my test method. So what I would do is go back and then take a look and review the results and take a look at just how many results are actually at risk if we know that we have this type of a bias in the system. So that may require that you actually need to run some additional QCs. You need to fix the error and then run some more QCs so that we can characterize what was the error state that I tested these patients under, and what's the bias between that and the corrected state. And at that point, we can then take a look at and judge, okay, what's the probability that these patients are actually going to have air conditions that are going to have a clinical impact. And that's what you would look at. Now, it gets tricky simply looking at the QC results in the context of the total allowable air condition, because these are individual points. And so you can have, for instance, half of your patient population be unacceptable and still have a 50% chance of having a QC result within that total allowable air condition. So it gets a little bit complicated, but in general, if you have a QC rejection that identifies a failure in your test method, then you need to correct the failure and then assess, did that failure produce patient results that that could cause problems clinically?
Mr. John Yundt-Pacheco, thank you again, sir, for your time today, for your important research. And before we go, I want to thank our audience members for joining us today and for their interesting questions, and questions we did not have time for today. will be answered and posted in the event resources by the end of next week. The webcast will be available on demand in the auditorium from Friday on. And if you found this informative and helpful, please share it with your colleagues. Bio-Rad will be hosting a new QC-related webinar every month this year. Next month's topic is the benefit of using an independent quality control, and will be held on October 21st. Please check back regularly on new topics and take care to explore our posters and our booths in the virtual conference. Until next time, everyone, take care and be safe.
Thank you. Bye.